Welcome back, everyone, to Computer Science 150. Today, we're going to take a little bit of a pause from the material that we have been doing recently. Recently, we've been talking quite a lot about objects and working with object-oriented programming. Although what has started to happen is I've started to get a little bit ahead of myself in terms of the lectures running a little bit ahead of what's going on in the programming exercises and the lab exercises. So what I'm going to be doing over the next couple of weeks is here and there, I'm going to be inserting some sort of optional material so that the labs and the assignments get a chance to catch back up with what the lectures are doing. All right, so before we go into today's lecture, just a quick reminder of what's going on this week. So first, we have a programming assignment due on Tuesday. This is a programming assignment that deals with some very basic aspects of creating and using objects. Also, the lab this week is going to focus on the basics of working with objects. That will start the process of getting you folks in the mode of thinking about working with and using objects in the code that you write. All right, so in today's lecture, what I'm going to be doing for most of the lecture today is I'm going to be talking about some optional material. The motivation for showing this material is that a certain portion of the students in this class are planning to major in computer science. And especially for those folks who are planning to major in computer science and planning to take more computer science classes, there is some core material that I would like to cover in this course that whenever we have an opportunity to cover it, I'll be doing that. Now, for the rest of you, the folks who are not necessarily going to be majoring in computer science and maybe just be taking this one course, you are certainly welcome to treat this material as purely optional. The material that I'm about to show you in today's lecture is not going to appear on any exam. It's not going to appear on any assignment. So if you are not intending to be a computer scientist, you are certainly welcome to treat this material as additional and optional material. But again, for the benefit of those of you who are thinking of majoring in computer science, I'd like to show some of this material because some of these things are sort of core concepts in computer science that every computer scientist should see at least once in their career as they're going through and studying computer science. All right, so once again today, the topic is going to be sorting. Now, we've had some discussion already of sorting, and I want to start by going back and reminding you of some of the things that we've done already in this topic. All right, so a while back when I was talking about the basics of working with arrays, I had an initial lecture where I discussed some techniques for sorting arrays of numbers. And in that lecture, we met two basic but very important sorting algorithms. The first and simplest sorting algorithm is selection sort, which I covered in an earlier lecture. And then a little bit after that, I covered a more advanced sorting algorithm called merge sort. Right now, again, the motivation for showing two different sorting algorithms is that sorting is a very important task in computer science. It shows up in all kinds of different problems. And because it is such an important task in computer science, you want to make sure that you have a reasonably good solution to the problem of sorting a list of items. Right, and that is the motivation for showing multiple different sorting algorithms. And that is the first sorting algorithm that you'll look at, selection sort, is very simple and easy to understand, but its major downside is that it is relatively inefficient. The amount of time that it takes selection sort to sort a list of items is proportional to the square of the length of that list. And especially as the list gets very long, upwards into the hundreds of thousands of items, the time that selection sort takes simply becomes too long to be practical for sorting very long lists. So that is our motivation for wanting to find alternatives to selection sort and to find better sorting algorithms. And the first better sorting algorithm that I showed you in an earlier lecture is merge sort. I just want to quickly review some of the main ideas in merge sort. First of all, the one important idea in merge sort is merge sort is based on the idea of breaking a list of items that need to be sorted into two smaller lists, dealing with those lists separately, and then bringing them back together. And the key steps in the merge sort algorithm are the steps where you take your original list, whatever it happens to be, and the first thing you do is you make two copies of the two halves of that list, right? So the first, you make a copy of the first half of the list, then you make another copy of the second half of the list, and then using a process called recursion, you actually call the merge sort process on those two shorter lists, hoping that merge sort will correctly sort those two shorter lists. And then the last thing you have to worry about is merging the two shorter lists back together to make a larger list. All right, now, one of the advantages of merge sort is that it is significantly more efficient than selection sort. Again, the time that selection sort takes to sort a list of n items is proportional to n squared, whereas the time that it takes merge sort to sort a list of n items is proportional to n times log n. And for extremely large lists, that is significantly faster than what selection sort is able to do. And that's our main motivation for introducing merge sort. Okay, now, having said that though, merge sort itself has a problem, and this is a problem that we would like to try to work around in our next version of the sorting algorithm. And the problem in merge sort is this: because you do have to make copies of the two halves of the list, so you can go off and sort those two copies and then merge them back together. One weakness of merge sort is it requires extra space, right? Because what you need here is both the space to store the original list of numbers, but you're also going to need an equivalent amount of space to store the two copies that you're making in the process of doing the algorithm. Right? So when people criticize merge sort, one of the main problems that they point out with merge sort is that it is not as space efficient as it possibly could be, because to sort a list of n items, you have to make these copies, which means that you end up taking twice the amount of space than is theoretically necessary to sort a list of numbers. And that is widely considered to be the main weakness in merge sort, just the fact that it takes extra space to store these extra copies, which makes it less than ideal as a sorting algorithm. Right, so that is basically the motivation for us to want to do better and to come up with an even better sorting algorithm. And the main characteristic that we're looking for in any better sorting algorithm is that it should be at least as fast as merge sort, and it should not use any extra space. Ideally, this new sorting algorithm should be able to do its work by just having the original list of numbers and then rearranging things within that list without having to copy anything to an extra list and use any extra space in the process. All right, so the next sorting algorithm that I'm going to show you today has both of those characteristics. It is very fast, like merge sort, and it doesn't use any additional space above and beyond what is already taken up by the space that it takes to store your items. All right, so let's put away merge sort and bring up the code for the next sorting algorithm that we're going to look at today. And this is a sorting algorithm known as quicksort. This is a very famous sorting algorithm in the world of computer science, because this was widely recognized as one of the first really good sorting algorithms that people have available to sort lists of items. All right, now, here are the main ideas that quicksort is based on. The first idea it's based on is a concept of what's known as a partition. And what happens in a typical partition is that you take a list of items and you partly sort this list of items. All right? And here's what we mean by partly sorting. What we're going to be doing is we're going to be taking a list of items, and the first thing we're going to do is we're going to go to the end of that list and identify one of the items as a special thing called the pivot value. All right, so whatever number currently happens to be sitting at the end of the list, we're going to give that number a special role. It's called what's called the pivot value. Right now, the job of the partition algorithm is to rearrange the numbers in the list so that when the partitioning process is done, what you end up with is all of the numbers that are less than the pivot on one side of the list, all of the numbers that are greater than the pivot are on the other side of the list, and in the middle, we drop in the pivot value. Right now, what that accomplishes is that gets the list closer to being sorted, but the partition operation doesn't necessarily aim to end up with a nicely sorted list. The only thing it tries to do is it tries to get you closer to being sorted by ending up with a list of numbers that are all smaller than the pivot itself, and a list of numbers all bigger than the pivot. And the two lists on either side of the pivot do not necessarily end up being sorted by this process. All they end up doing is basically being divided into two groups, which gets you closer to a sorted list, but doesn't get you all the way toward being sorted. Okay, so let's take a closer look at the partition method and see how it does its work of reorganizing the numbers into small numbers to one side and big numbers to the other side. Okay, now the main thing that the code here is attempting to do is it's basically attempting to find all of the small numbers and move them over to the left. And as a side effect of moving all of the small numbers over to the left, you're going to end up with all the larger numbers ending up over to the right of the list. Right, so most of the action here is driven by a single loop. This loop basically scans the list from whatever you consider to be the start to the end of the list, and it's going to look at each of the numbers in the list exactly once. Okay, now what it's looking for as it does this scan is it's looking for small numbers. So if it comes across any number that is less than or equal to the pivot, that's considered to be a small number for our purposes here. And what we want to do with those numbers is we want to move them over to the left end of the list. Right, so to help us with that process, we're going to have a second index. This other index is called I. And at start, that index starts out before the start of the list. And each time we identify a new number that wants to go over to the left-hand side, we're going to increase that index by 1 and then basically carry out a swap. We're going to make two items change places in the list. We're going to take this small number that we've just located and we're going to move it over to the left side of the list. So that basically is going to go to position I. And whatever was originally in position I is going to get swapped into position J. And this single swap accomplishes two things. One thing that it does is it takes the small number and moves it over to the left. But then also as a side effect of doing that, it will also end up picking up a large number and moving that over to the right where the large numbers want to be. All right, so all it's going to take is a single pass through the list, identifying any small numbers that we can find. And anytime we find a small number, we make it trade places with a big number. And the net effect of having done that all the way through is you end up with all the small numbers to one side and all the large numbers to the other side. But each of those groups are not necessarily sorted after this process is done. All right, and then the last thing you need to do is when this process concludes, the index I will tell you something useful. At that point, I will tell you the location of the last small number, and the number that is at location I plus 1 is the first of the big numbers. And what we're going to do at the end of the process is we're going to take the number that sat at the end, which is actually the pivot. We're going to make that trade places with the first of the big numbers. So the net result of that is you end up with the small numbers, the pivot, and then the big numbers, and that's the order that we want things in at the end of the process. All right, and then finally, besides rearranging the numbers, the other thing that the partition method does is it returns the location of the pivot when this operation is done. All right, so that is the partition step. This is an essential building block for building a sorting algorithm, and it plays a key role in the algorithm that we're about to see. All right, so let me pause here and ask if anybody has any questions about how the partition operation itself works. Okay, now, partition is just a building block for the sorting algorithm. The main sorting algorithm is going to be implemented by this next method, which is called the quicksort method. And the purpose of this quicksort method is to take a list of data items and some portion of that list, basically from location start up through location end. And the job of quicksort is to successfully sort all of the numbers in that range. Right now, the first thing that quicksort does is it takes a look at how large the range is. And one sort of detail that we can set as a parameter of this whole operation is we can set a threshold value. In this class, the threshold value is actually declared as a member variable. We set initially the threshold is set at 40. And whenever the range that we're asked to work with, the portion of the list, whenever that is smaller than 40 items in size, we don't bother to work particularly hard with that. Instead, we simply hand off the work to selection sort and say, hey, we're dealing with a chunk of numbers that's small enough that even you can handle this reasonably well. So we're just going to pass the buck off to selection sort anytime we have to deal with a list that is small enough, that falls below our threshold. Now, if instead, if we're asked to deal with a range of items which is large enough that it's not below the threshold, then we're actually going to be doing our quicksort process. And the first step in the quicksort process is to call the partition method on that portion of the list. And again, what partition will end up doing is it will end up partly reorganizing those numbers, and it will also tell you where the pivot landed after you did that partitioning operation. All right, now, once we've done the partitioning, that sets up a classic example of what we call a divide and conquer strategy, because what happens next is we take the two halves that were created by the partition. The first half goes from start to right before the middle, and the second half goes from right after the middle to the end, and we, by a process called recursion, we call the quicksort algorithm on those two halves, and it goes to work further organizing those two halves. And after enough rounds of partitioning and further calls to quicksort, we end up with the entire list completely sorted. All right, and finally, the two most important things to note about this algorithm is it turns out that this algorithm has roughly the same efficiency as merge sort. It also will sort a list of n items in time that's proportional to n log n. And a greater advantage that quicksort has over merge sort is that quicksort doesn't need to make any copies of the numbers. It does all of its work by just simply rearranging the numbers within the list that you've given it, and that makes this algorithm very space efficient. All right, so this has now two very good characteristics. It's both time efficient and space efficient, and this was one of the first sort of general purpose high performance sorting algorithms that was developed in computer science. Right, and again, this is one of those classic algorithms in computer science that every computer scientist should see. So that's one of my motivations for showing you this algorithm today. All right, so that is the quicksort algorithm for sorting lists of numbers. All right, now any questions at this point about how quicksort works and what it does? Okay, now the next thing I want to do today is, now that we have yet more sorting algorithms, even better sorting algorithms, the next thing I want to talk about is one classic application of sorting. And what we're going to talk about next is another very common problem in computer science, and that is the problem of searching for something. Right? Suppose you're in a situation where you have a very large list of numbers, and somebody comes along with a number and asks you, does this number appear somewhere in the list? Right, now you have two options for answering that question. The first and simplest option is to do what's called the linear search. In a linear search, all you simply do is you set up a loop that goes from one end of the list to the other, And at each number it comes to, it simply checks to see if that is the number you're searching for. And if you come across the number that you're searching for, you'll immediately stop and return true, saying, yes, I've established that this number is in the list. Okay, now linear search has both a strength and a weakness. Its strength is that it will work on any list, whether or not the list is sorted or not. Its other great strength is that it is very simple, it's very easy to write out and very easy to code. But the greatest weakness of linear search is that, especially for very long lists, this process can be very slow. For example, if you have a list with 1 million items in it and you're searching for a number which appears somewhere in the list but somewhere near the end, it's going to take you a very long time to scan through all of those hundreds of thousands of items before you actually find the thing that you're looking for. And that is linear search's primary weakness. It's relatively inefficient. Right? Well, that's what motivates us to find another strategy for searching for things. And this new strategy that I'm going to introduce you to today is also a very famous strategy. It's called binary search. Okay, now binary search is a very fast and very efficient way for finding things, but binary search has a specific requirement, and that is binary search will only work on lists that have already been sorted. Right? Because binary search takes explicit advantage of the fact that the list is sorted to do the search much more quickly and efficiently, and you can only use binary search on a sorted list. Right? So that in turn is why it's important to have an efficient sorting algorithm like Quicksort, because if you can use Quicksort to quickly sort your list into nice sorted order, then binary search can come along and take advantage of the fact that the list is sorted to do searches very quickly and very efficiently. All right, so here now is the code for binary search. And again, it's in the form of a method where you hand it a list of numbers and a number you're searching for. And what this method will attempt to do is it will attempt to find where the number appears in the list, and it's going to return the location of that number in the list to you, right? So once it finds that number, it's going to make note of the index where that number is located, and it's going to return that index back to you as the result of the method. All right, now here's the strategy behind binary search. It's basically based on the idea of repeatedly cutting the list in half. So at the beginning, the first thing that we do, in fact, the very first thing that happens in the logic for binary search is we figure out where the middle of the list is located. Right? We do that with the help of a couple of other variables, the start variable and the end variable. At start, the start variable points to the first location in the list. That's always location 0. And the end variable points to the last location in the list, which again, remember in a zero-based system, that's always the length of the list minus 1. Right, now, the first thing we're going to do once we've established where the list begins and ends is we're going to figure out where the middle of the list is. Right, and that's an index that you can compute easily just by taking the average of the start index and the end index. Right, now what we do next is we take a look at what's sitting in the middle of the list. And there are going to be 3 possibilities for what's happening at the middle of the list. The first possibility is that we just get wildly lucky and we go to the middle of the list and we discover, oh, look, there's the number we're searching for. We found it. Okay, now there's one additional thing that you might want to do in this case. And that is, you might want to take advantage of the fact that the number you're looking for may appear more than once in the list, right? So as a follow-up to that, if you land in the middle and the number you're looking for is there in the middle, the next thing you should do is run a simple loop that basically goes backward from there, basically checking to see if there are more copies of that same numbers off to the left. So what we're going to do is basically run a simple loop that backs up one place at a time as long as we keep seeing X's, right? Because what we're looking for here is we're looking for the first place in the list where that X appears, right? This list will take care of finding that first location, and then when you found that first location where X appears, you return whatever that location is. All right, so that's the first possibility for what could happen when you look at the middle. You could get really lucky, and when you look at the middle, there's the number you're looking for. And with a little bit of extra work, you can finish your work at that point. Okay, now in most cases, that's not going to happen. When you look at the middle of the list, you're not going to see a number that is equal to the thing you're looking for. So we have two remaining possibilities. One remaining possibility is that the number in the middle is less than the number that we're looking for. Okay, now let's think about what happens in that scenario. Suppose you go to the middle of the list and you see a number sitting there which is smaller than the number that you're searching for. Now, one thing that you can immediately judge based on that is that since the list is sorted and you're looking at a number that is smaller than X, one of the things that you can tell is that all of the numbers to the left of that middle point are also going to be smaller than X, which means that none of those numbers are interesting to you. Now, that's actually a useful thing to know because that means at that point you can ignore literally half of the list. And the way that you ignore that half of the list going forward is basically by readjusting what your start point is considered to be. What you do is you reset the start point so it starts right after the middle, because you know the number you're looking for is not at the middle, it's also not before the middle. So by moving the start point past the middle, you can effectively ignore half of the list. Right? And by the same token, if you go and look in the middle and the number sitting in the middle is bigger than X, in that case, you know everything from that location all the way to the end is also going to be bigger than X. So you can ignore those numbers. And the way to ignore those numbers is simply moving where the end of the list is up to some place that's to the left of the middle. Right? So regardless what happens here, either we're going to find the number we're looking for, or we're going to be able to throw away half of the list, right? That's making major progress toward reducing the number of things that we have to search. All right, and then the only thing we need to do beyond that is put all of this logic inside a loop, so it keeps going multiple times. We're going to go
I
for
love you too.
multiple rounds. We're going to keep doing rounds, and in each round, what we're going to do is we're going to either find the number that we're looking for, or we're going to be able to throw away half of the remaining numbers. Right now, if you keep throwing away half of the remaining numbers, very quickly you're going to have not very many numbers left to search in. And eventually what's going to happen is you're very quickly going to narrow down to the place in the list where X will be. And after a few rounds of this, you will probably end up landing right on the number that you're searching for. And at that point, the search will conclude. Right now, the only remaining possibility here is that the number that you were asked to search for may not actually be in the list. And what will happen there instead is that if you repeatedly keep throwing away half of the numbers, eventually you're going to arrive at a situation where there are no numbers left for you to search in. And that's what the test in the while loop is looking for. It's basically looking for a situation where you have no numbers left to search in. And if you have no numbers left to search, that means that the number you're looking for isn't there and you're not going to find it. And the only thing left to do is to return some sort of an answer at the end. Well, what we do in that case is we basically, if we can't find the number we're searching for, what we do instead is we return the location of the first number larger than X. Right? So for that, there's a little bit of logic at the end, which handles the case where X is not in the list. And if X is not in the list, we simply return the location of the first number, which is bigger than X, which also may be useful to know in some applications. Right? And because this binary search algorithm works by basically repeatedly cutting the list in half, it can very quickly conclude its work. In fact, a mathematical measure of how efficient this algorithm is that if you give it a sorted list with n items in it, and you have it run its search, usually the search concludes in a time which is proportional to the log of n. Right? And even for very large numbers, like a million items in a list, the log of that size is not terribly big. That's on the order of maybe 10 to 12. So that means that it only takes you about 10 or 12 rounds to either find the number you're looking for in a list of 1,000,000 items or establish that it's not there. This is a very fast and very efficient search algorithm. Right? But again, the main requirement is that you can't take advantage of this binary search algorithm unless you have sorted your list to begin with. And that is why you need a relatively efficient sorting algorithm like Quicksort to help you out in doing this searching process. Okay, any questions about binary search?
I do have a question, sir.
Yes.
So when we are dividing the list into half and it just so happened that the value we are searching for is in the middle, why are we only testing if the value come before it is also the value we are searching for, but not the value, not the position in front of it?
Well, again, it has to do what the overall goal of this algorithm is. And the goal is to, first of all, if the number is there, what we want to report is the first location where it appears.
Ah, I see.
So that's why if I do find it, I don't immediately say, oh, it's right there in the middle. What I have to do instead is, because there may be multiple copies of that number, what I have to do is do a little bit of a search off to the left to see if there are more X's to the left. And what I want to do is find the first of those X's and then report where that was located. That's why we do that.
Oh, gotcha. Because I mistakenly assume that we are listing all the position of X.
No, we only want to return the first location where X appears.
All right, gotcha. Thank you.
Okay, so that is the main thing that I wanted to do for you today. Again, just a sort of bonus material. I wanted to introduce all of you to Quicksort and binary search. These are two very famous algorithms in computer science, and certainly if you're going to be majoring in computer science, you're going to be meeting these algorithms at multiple places in your career. And I wanted to introduce these because they are so famous and so widely used in computer science. Okay, now, the other thing that I want to do today is something that will be of interest to everybody, and that is I want to also say a little bit something about objects again, because we are still in the portion of the course where we're mostly dealing with
What?
object-oriented programming. And what I want to talk about briefly next is how to sort lists of objects. Because in all of the examples that I've shown you so far, I basically have been using lists of integers for my examples. That's a very important case, but that doesn't cover every scenario where you might want to sort things. Because in some applications, what we're actually going to find ourselves having to do is sort lists of objects, right? And that's going to become more and more common as we do more and more programming with objects. We're going to be writing more and more examples of programs where our data is going to come to us in the form of a collection of objects that are stored in some sort of a list. And in some applications, we may want to sort those objects to achieve a particular effect. Right, so to show you how to do that, I brought along one of my earlier examples. This is the example that I showed on Friday. On Friday, I showed an example of the produce tracker. And one of the things that the produce tracker does is at the end of the day, it's supposed to print a report of what items you have in stock. Now, in the version that I showed you on Friday, when it printed that report, the items came out in no particular order. Right? Well, something that you may want to do when you print a report is you may, for example, want to have the items that the report prints printed in alphabetical order. Right? So what I've done is I prepared a new version of the produce tracker program, and when you run it, it will print that report at the end of the day, but it now does one additional extra thing, and that is it also alphabetizes the items so that when it prints the items in the report, it prints them in alphabetical order. Right now, to be able to put that list in alphabetical order, we need some basic mechanism for taking a list of objects and sorting it by the names of those objects. And that process is going to require two things. The first thing it's going to require is some sort of a sorting algorithm. Right? And I've embedded the sorting algorithm into the print report method. So if we go and take a look at the inventory class, we'll see that I made one small change to the print report method. And that is I've added an extra line of code that is designed to take the list of items that we have and sort them. All right, now for this, I've taken advantage of the fact that out in the Java class library, there is already a sorting algorithm available, and this more specifically is a sorting algorithm that works with array lists. Because the data that I'm working with in this example is stored in an array list. This stock variable is an array list in which we're storing items. And anytime you want to sort an array list of objects, you'll want to have a sorting method that is designed to do exactly that. All right, well, to help you do that in Java, there is another special class. It's called the collections class. It's found in the java.util package. It's the same place where the array list class appears. And one of the things that's in that collections class is a static method that you can use to sort array lists efficiently. It's simply called sort, and it uses a very efficient sorting algorithm to sort the items in an array list. Okay, now, unfortunately, this is not the only thing you require to make this work, because if you're going to successfully sort a collection of objects, you need to do one additional thing, and that is you need to add some extra code to the objects themselves that makes it possible for the sorting algorithm to work with those objects. All right, and in this case, the objects that we're talking about is that in my stock list, I have stored a collection of item objects. So to make it possible to sort that list of items, I have to go to the item class and add one additional thing to make it possible to actually sort those things. Right? And the additional thing that we need to add to make this work is we have to add a specialized method to our item class. Right? And this method is called compare_to. And the way that it works is it's meant to be applied to an object, and it also takes a parameter, and the parameter is some other object that you are trying to compare to this item. Now, what the compare_to method is supposed to do is it's supposed to return an integer. And there are three options for what that integer can be. If you compare yourself to this other object and you think that you two are essentially equal as far as the comparison goes, then in that case, you're expected to return the value of 0 to indicate that the two of you are the same. Now, on the other hand, if you compare yourself to this other object and you think that you should come before this other object in some sort of ordering, in that case, you have to return the value of -1 to indicate that I come before this other thing. And the third scenario is that if you compare yourself to this other object and you think you should come after this other object in some sort of ordering, in that case, you have to return the special value of +1 to indicate that you come after this other item. Okay, now that's the only thing that's required of this compare_to method. You have to return -1 if you come before the other thing, 0 if you consider yourself the same, and 1 if you consider yourself larger than. So all you have to do in the method is put some logic that will return one of those three values depending on how you want to arrange yourself relative to this other thing. Okay, now, when it comes to deciding how you should arrange yourself relative to something else, there are basically different answers to how to do this for each different class that you create. Essentially, what you have to do in each one of these cases is look at the data that's stored inside the class and ask yourself, does this data give me any natural way to put things in some sort of a natural order? All right, and in this case, because each item contains both a name and a quantity, you could conceivably put things in order by using either the name or by using the quantity. It's up to you. And whatever decision you make, you're going to code that logic into the compare_to method. Right now, for this particular application, because I do want to sort items by name so that when we print the report, we can print the items in alphabetical order, I do want to focus on the name as a means of putting things in order. Right now, that's also fortunate because the name is a string, and it turns out that the string class itself already has a built-in compare_to method that you can use to compare strings. If you have a couple of strings, for example, if you have your name and the name of some other item and you want to compare them, you can take advantage of the fact that the string class already has a compare to method. And the way that compare to method works is it uses alphabetical order to determine the ordering, right? So if your name comes before this other name alphabetically, the strings compare to method will return -1. And if your name comes after this other name alphabetically, then the strings compare to method will return +1. Right? So if we want to use the names as a basis for putting these items in order, all we have to do is compare the names of ourself and this other object using the strings compare to method, and that will give us the right value to return. It'll return either -1, 0, or +1 based on how these two names are relative to each other in alphabetical order. And since that's the ordering that I want to put things in, that's the right way to set up the compare to method for my item class. Right, so that's the main requirement, is that you have to add a compare to method to your class. The other extra step that you have to do is you also have to notify the outside world that you do in fact have a compare to method. And the way that you do that is by adding an extra declaration to the class itself. We add this extra declaration that basically says that this is what's known as a comparable object, an object that is capable of comparing itself to other objects of the same type. And that's the way that you advertise to the outside world that you do in fact have a compare to method, so that others who need to can call this method for the purpose of doing comparisons. And once you're able to compare these objects to each other, you can do things like sorting. All right, so once you've equipped your item class with the compare to method, and you've notified the outside world that you do in fact have a compare to method, then you can put a collection of these things in an array list and then sort that array list using a standard sorting algorithm, as we see being used here. All right, so those are all the things that are necessary to make it possible to sort a collection of objects. Once you've equipped those objects with the compare to method, you can then hand a list of those objects off to this sorting method, and it will then be able to do the right thing. It will be able to sort them into the order that you want using the comparison mechanism that you have provided. All right, so that now solves the problem of being able to sort array lists of items or anything else. So going forward from here, anytime we need to do a sorting process on a list of objects, we now know how to do that. Okay, so any final questions about the object sorting example here at the end of the lecture? Okay, well, if not, with that, we are out of time for today. Again, that's the extra bonus material that I wanted to show you. I wanted to talk a little bit more about sorting. And at the end, I also wanted to tack on some material to show you how you can successfully sort a collection of objects, because this is a thing that may well come up in later problems that we do in this course. All right, so that's all for today, and we'll see you all back either in lab or lecture later in the week. So have a good day until then.
Thank you.
You're welcome, everybody.